Hello everybody and welcome to example 3 on page 37. So hopefully you've taken a little bit of time to actually work through this example and do these calculations. I'm kind of showing you my partial calculations so that you can compare with the answers that you got. Okay, so over here on the left, that's our calculations of powers of alpha, trying to determine how many powers do we need to take basically to get back to the identity element. Okay, and you can kind of see from the calculations here that 6 was the lowest power of alpha that got us back to the identity element. Okay, and so from that calculation we can see that the order of alpha is 6. Okay, now I want to talk about a couple of things. You might have noticed these things as you were doing these calculations. So first of all, for example, if you look at the first line here where we were calculating alpha squared, the two permutations 1, 3, and 2, 4, 5, those are disjoint cycles, and so you might notice that you could reverse the order of those two permutations. Noticing that makes this calculation easy, because if you make that switch, you've got 1, 3 composed with itself, which is going to be the identity, okay, because you've got a 2 cycle composed with itself. And so really, all you had to do that calculation was to take 2, 4, 5 and compose it with itself, because the 1, 3's went away, and that's where the 2, 5, 4 came from. Okay, and that type of observation is useful in a couple of places, okay, when you do your calculations of the powers of alpha over here. Now what about beta? Okay, kind of the same thing. So if we look at this line over here, beta squared would be the permutation beta composed with itself. There, we've got disjoint cycles again. 3, 4, and 1, 2 don't have anything in common, and so we're allowed to reverse the order. Okay, that's what the previous theorem said. Okay, what was the number on that theorem? I'm going to take a peek back. Okay, that was theorem 5.2. That's what's allowing us to do that order switch. And then notice that we've got 2 cycles multiplied by themselves, so we're going to get the identity there and the identity there, and that tells us that we're just going to get the identity permutation, and we've just confirmed that the order of beta is equal to 2. Okay, now I'd like to talk about how this leads into the next theorem. Okay, that was quite a bit of work doing those calculations, and so I'm wondering if we could notice a general pattern here that would prevent us from having to do so much writing every time. Okay, and the thing that I'd call your attention to is that with alpha, we started with 2 disjoint cycles, and the length of the first one was 2, and the length of the second one was 3. Length 2 and length 3. Notice that the 6 that we got is the least common multiple of those two numbers, the least common multiple of 2 and 3. This might remind you of a theorem that you saw back in a previous chapter. It was either chapter 3 or 4. Okay, kind of a similar thing is going on here. Okay, and the same thing happens with beta over here to the right. Okay, in that case we've got cycles of length 2 and 2. Okay, in both cases. And the 2 that we got is the least common multiple of 2 with itself. Okay, so here's what we can say in general. Okay, we won't prove this theorem together, but you're welcome to look at the written notes and kind of look at an outline of the proof if you're interested. Okay, and this allows us to determine the order of a permutation that's in disjoint cycle form. Here it comes. So the order of a permutation of a finite set written in disjoint cycle form, and I want you to underline that. That's very important. To use this theorem, we need to have it in that form. Okay, and if it is in that form, then the order is always going to be the least common multiple, okay, of the lengths of the cycles that make up the permutation. Okay, and this is an observation that could be very useful to you when you're trying to determine the order of a permutation.